Hello again. It's my pleasure to introduce Rafael Potrie from Instituto de Matemática, who's going to talk about attractors derived from Anosov diffeomorphisms.
Thank you very much. So it's on. Okay. So it's a pleasure to be here. I'd like to thank the organizers for this honor, and it's a pleasure to be celebrating Marcelo's birthday. So, in fact, my work is very influenced by Marcelo's work. In particular, his book with Lorenzo and Cristian was very important for me. And IMPA has a big impact in mathematics in Latin America, and also Marcelo is a big part of it. So the problem I'd like to discuss has to do with attractors of partially hyperbolic diffeomorphisms, which is something that also appears a lot in Marcelo's work. And I will try to explain a result that has to do with topological attractors, but it has some relationship with results on ergodic attractors, and I will try to comment on that too a little bit. So let me say, the context, I wrote it here, so I will work in closed tree manifolds to simplify many things, and consider partially hyperbolic diffeomorphisms, which are like a flexibilization of hyperbolic diffeomorphisms, and there are many questions we still don't understand about them. So the problem I'm interested in is in finding conditions to understand where orbits go for a partially hyperbolic diffeomorphism. So let me say something about what I mean by attractors. So, and this distinction already appeared in Benedict's talk on Monday. And there are two kinds of attractors that I'm interested in. There are like topological attractors. And by this I mean there exists an open set, a non-empty open set, such that it's trapped by the dynamics. So the closure is sent into its interior, and then the attractor would be the intersection n is bigger than 0 of the iterates of U. So this is a compact NF invariant set. Compact. And the important thing when you are dealing with partially hyperbolic diffeomorphisms, this set here is saturated by unstable manifolds. And then there's the notion of ergodic attractors. That, as we've seen this week, it's very important in Marcelo's work. And these are ergodic measures with basing of positive Lebesgue measure. So, of course, there are, in the partially hyperbolic setting, these are sometimes also called SRV measure. These appear this week too. I won't define precisely, but we first need to locate the place where to find them, and topological attractors are a good place to do. So in this talk, I will focus mainly on topological attractors, and the questions I'm interested in are like existence, but so the definition I gave is pretty weak. So for instance, existence is guaranteed by the fact that the whole manifold is always an attractor for in this sense. But so the question is existence of proper attractors. So where and then you can wonder about like finiteness or uniqueness results. And so to motivate the question, let me say that in the typical case or the generic case, finiteness can be approached in a different way than the problem I'll be interested in. So let me state this is a result joined with Sylvain and Martin Marino, which says that for a C1 open and dense set of partially hyperbolic diffeos, there are finitely many disjoint attractors. But, and of course, in general, one cannot improve this density property because you can construct by hand examples. For instance, you take Anosov times something in the circle which has infinitely many attractors. So this cannot be improved in this sense. And so my question is whether adding some topology to the problem allows you to improve this kind of results. So I will state some known results.
Sorry, and Rafael, what about the subtle? It's not that they are also finite.
The what?
The subtle set.
No, it's not. So this is unknown. So this is
Only for attractors.
yeah. So this is related to a conjecture by Pallis, and finiteness is only understood when you have. So the gain is this, right? So we have this will appear in the talk. So since we have this, the attractors already have some definite size, and it's easier to show that if you can have finitely many disjoint ones. Okay, so yes, and all the results I will state depend very strongly on the fact that you are unstably saturated. So some results. So here there's an example where you can produce infinitely many attractors, and this is what's called a skew product. It's something that fibers over an Anosov diffeomorphism. If the skew product is somewhat twisted, then this kind of example cannot exist. So if M is a non-toral nil manifold, and this appeared in Chagrin's talk, then there exists a unique attractor, and this is joined with Andy Hammerlindel. And this attractor can be proper. This is E-schist thesis. Similarly, you can wonder about partially hyperbolic diffeomorphisms which look like Anosov flows. So there's four. This is called discretized Anosov flows, which are like a generalization of perturbations of time one map of Anosov flows. Then, assuming that the Anosov flow is transitive, then you also have uniqueness. And this has been proved by Rodriguez Hertz and Ures in Hanna Rodriguez Hertz and Ures in the perturbation of time one map. and with a different proof in the general case by Wellman and Martin Chich. And again, in this case, the attractors can be proper. This is quantity. And so there are other classes of partially hyperbolic diffeomorphisms, and from the classical classes, the one that I have not mentioned yet is the class of derived from Anosov diffeomorphism, which is the title of my talk. So let me first say, when F is derived from Anosov, and this means that the action of F in the homology, or the fundamental group, so this is a map from T3 to T3. So the action in homology, which is C3, is a hyperbolic matrix. Then uniqueness is known, but we didn't have any example of a proper attractor. So the result I want to discuss is a joint result with Sylvain, which says the following. Isotopic to Anosov. So this is exactly that definition I said there. Then if U is non-empty and it's an attractor, then U must be the whole torus. So, and this is not a very difficult thing, so I will try to explain the proof. But before, I want to make some comments. No, this implies, yeah, that's an important point. So this is equivalent to saying that the whole manifold has to be chain recurrent in general, and one could certainly ask whether this implies that every such partially hyperbolic diffeomorphism is transitive. So we still don't know. What we do know is that open and densely, it has to be transitive. Okay, and maybe it is always transitive, but what I will explain today is not enough. Okay, so it just tells you about this property. So it cannot attract a set, but still there are some things to understand. Okay, so the comments I want to make before I enter into the ideas of the proof. First of all, so there are other classes of partially hyperbolic diffeomorphisms, even in dimension 3. And for those classes, all this question makes sense, and we have very little progress. And so that's something I find interesting, and there's work to do. And also, I want to relate a little bit the problem, because so the solution or the proof interacts with ideas that have been developed to understand like unstable minimal laminations of partially hyperbolic sets, and have to do with these ergodic attractors and SRB measures. So let me state one general result in this direction, and that kind of motivated these two. Let me see. So in fact, the proof of this theorem is inspired by a recent idea by Avila, Corbisier, and Wilkinson to get minimality of strong and stable foliations of certain diffeomorphisms, and that has to do with the following result, which I think it's pretty clean. It's a result joint with Avila, Corbisier, Wilkinson, and Sang, that says the following. So let F be a C1 plus Anosov and with splitting T3. So here it's partially hyperbolic, but the center direction is uniformly expanding. There are some weakenings of this, but this is a general statement. Then the strong and stable foliation, that means the one tangent to this bundle, is minimal. And if F is smooth and ES plus EUU are not jointly integrable, then there exists a unique U state which is SRB. Okay, the reason, so the idea that I will borrow is the first part, so how to produce minimality, but I wanted to say this to promote this result by Asaf Katz and parallel a result by Sebastián Álvarez, David Obata, Martin Leguil, Bruno Santiago, that started to apply techniques in measure rigidity to partially hyperbolic diffeomorphisms. Okay, so now I will try to use the rest of the time to discuss the main points of the proof. See, this is weak and stable, and this is strong and stable. So this is always integrable, but this is very unlikely to be integrable. So this is so this means not being accessible, essentially. It's
because the first U looks like a W.
Yeah. Sorry. Yeah. Okay. So what's the main tool? So first.
Did you say that the extremal ones, in general, they are not showing integrable?
No.
So what happens when they are not?
When they are not, then you have a unique U state, which is SRV. So it's are not. Yeah. So this is maybe in this case also there's a unique U state, but this case we still don't know. but this case is the most unlikely case. Okay. Okay. Thanks. It's what? Yeah, so in which case, sorry?
The meaning of U state.
SRV, sorry. SRV means being absolutely continuous along these two guys, and U state means being absolutely continuous along this guy. So essentially this is promoting being absolutely continuous here to being absolutely continuous here. But so the point is that being here makes your measure physical. So and here it's so it's a digression. So measures which are absolutely continuous here always exist, and absolutely continuous here is not so clear. So the point is to take one that exists and try to promote it to one that you are looking for. Okay. Yeah, so here it's Anosov, so this one exists, and so you are showing that it's always the same. But yeah, and so the point, these kind of techniques are still have some flexibility, and one hopes to be able to go further. Okay. Okay, but so I come back. I need to present some short tools in the proof. So the first is Frank's semi-conjugacy. And in this case, what we have is that there exists some map, so H, continuous, anomatopic to identity, which semi-conjugates, so you have T3, you have your F, and your F is an extension of the linear map. Okay, so let me call the bundles. So A is a linear Anosov with bundles E as A, E weak unstable A, strong unstable A. Okay, and this map is homotopic to the identity. This means that lifted to the universal cover is bounded distance from identity. Okay. Then the second tool is that we need to understand for F. So so here we have this F, which is so it's convenient to try to see whether this splitting induces some foliations in the manifold. So there are invariant foliations. So the second tool is the invariant foliations. And this goes back to the work of Brin, Ivanov, and joint work with Andy Hammerlindel, which says that there are foliations. There exist foliations tangent to CS, to CU, see, even if you go even backwards, so I already mentioned, so the stable and unstable foliation are more classical. You have all these foliations for f, and you also understand pretty well how do they interact with the foliations of the linear part. Okay, so the map H, let me do it in the universal cover, but then these maps CS and CU, CS of F, goes exactly to, in a point X, say, it's ES. And the same happens for CU with WU, WU. And you also have the following properties. So and here it's important to see that this is not really a symmetric argument, because the linear part here, I'm assuming that it has a weak unstable direction. So it's not the same when you look at the stable direction that the unstable direction, and it won't be the same to look at attractors than to look at repellers. And so the point here is H, when restricted to the stable foliation of F, is equal to the stable direction. So but this is not true for the unstable. In the unstable, all you know is that H maps the strong unstable foliation of F is contained in the unstable direction. And it's injective when restricted to this, but it's only contained here. And typically, you expect the image to be like a fractal graph. Okay. And now I will explain how these things interact with the attractor. And the proof will be by contradiction. So let's there exists lambda, a proper attractor. So F lambda is the intersection of Fn of U hat with and then you can define, so also have R you have a repeller here. So this one is WUF saturated, and this one is WSF saturated. And since these are compact invariant sets, which are distinct, we know that the distance between lambda and the repeller is bigger than some positive constant. The point is that when you look at the semi-conjugacy, so being WS saturated means that the repeller is mapped by the semi-conjugacy to the full torus, while the attractor could be a proper set when mapped to the semi-conjugacy. So we know that H of the repeller is the full torus, while H of the attractor is properly contained in the torus. This is because whenever you have this semi-conjugacy, you can show that there are points where H is injective. So since the distance is big and this contains everything, this cannot be everything. And the idea now is try to enlarge this set as much as we can to reach a contradiction. So let me say the statement I need, try to explain little bit. So proposition for every L you take any unstable leaf of the attractor, say, of lambda. So a segment of certain length bigger than some uniform constant, then, and let me work in the universal cover to simplify, then there exist points yc in L and n in C3 such that C plus n belongs to the stable manifold of Y, and the projection is A from, and then I need to go through the semiconductor. I will make a drawing now. So this is a bit technical. Of, this I could have made this global, but okay. Intersects both components of well, let me make a drawing because this maybe says nothing. So what I'm saying is I have an unstable segment of sufficiently long length. Then I look after the semiconjugacy, and so I have here a potentially fractal curve. And what I'm saying is that I can find a point here Y and a point C, so that if I translate here to some other leaf, so this translation is just an isometry, so it maps this as a fractal curve here. So here is now C plus N. And then when I project by stable holonomy, this point goes here, and the image of this curve does something like this. It crosses this curve. So it's a transversality argument. Only that these are two fractal curves, and the idea to prove this, it's essentially, this is an important point. Essentially, if this curve were not fractal, then typically you expect these to coincide, and then you get joint integrability, and then this would map to the whole torus. And so typically you have a fractality, and then you see here a segment, and you draw a shortened curve here. And then translating and projecting is a minimal, it's a minimal system. So you can send this point into the interior, and this will force intersection, transverse intersection of the foliations. Okay. Okay. So now we have this, and with this the idea is that now I have these 2 points which are in the same stable manifold, and I want to iterate forwards until they are close by, and see that my attractor needs to have several layers in the same center and stable manifold. And that's the contradiction I will try to obtain. So let me express that in a proposition. So for every epsilon small enough, there exists a n uniform so that if I1, In are unstable arcs of the attractor, and so that we have 2 properties. The Hausdorff distance between the image of this interval, so I'm again working in the universal cover. So these intervals are pretty close. And the second property is that they have disjoint local stable sets. Okay, so this is actually, so the idea is what I was saying. So I want to construct many curves, one above the other in the same center and stable manifold. But for technical reasons, I want to avoid taking limits. And so I will essentially put a technical condition that tells me that they are one above the other and they project by the semi-conjugacy to different things. So this technical definition, which will be enough to run the proof, it's a proof by contradiction, is as follows. So I will ask the local stable set. So this is the condition. The local stable set are pairwise in the F side. These are disjoint, so we can say one is above the other locally. And then we also want that when I map them by the semi-conjugacy, they go to different places. So the H of I the local stable manifold of this intersects the center leaf of essentially what I want, I will have these 2 intervals here. I can think of them, they are very close, but when I look at the stable manifolds, I want them to be different, so one is above the other. But when I map them by the semi-conjugacy H, it could be that these 2 intersect at some places. But I just want them to be different, so that they intersect different fibers at some point. It's a technical condition. And then there exists n, so that there cannot exist intervals with this property. So essentially, the idea is that each time you have an interval like this, you are putting some delta direction inside the center, and since the semi-conjugacy is bounded distance from the identity, you are forcing a very big set to map into a very small interval. So the idea is to find as much intervals as this as you can. So this is very related to the argument of Avila, Crovisier, and Wilkinson, where they need to produce this and take limits. But for doing that, they need some distortion estimates and bounding properties of the holonomy so that they can equidistribute these intervals. But here, since it's just an argument by contradiction, you can stop at finite time and already get a contradiction. Okay, so let me end by explaining this argument by Avila, Crovisier, and Wilkinson, that it's like mixing this transversality property and iterating to the future. It's an inductive procedure. So let me say, so we'll use transversality to produce intervals. And the inductive procedure goes as follows. So let me hold property M epsilon means that lambda contains M intervals of length 1. Verifying these two properties. Okay, and so clearly, so property remark, property 1 epsilon holds for every epsilon. You just, the conditions are empty. And if you have condition M epsilon, then you have condition M prime epsilon prime for M prime smaller than M and epsilon prime bigger than it. And so the inductive procedure will be to show, so main point, if you have M epsilon for every epsilon, then so for every epsilon prime, if you have M epsilon for every epsilon, then you have M plus 1 epsilon prime. Okay? And so if you do this, you'll produce as much as you want. In particular, you'll reach the point where you contradict this. And so let me make a drawing to explain this procedure in the 2 minutes I have. So you fix epsilon prime, and you will take M epsilon with epsilon much smaller than epsilon prime. So you have, since epsilon is much smaller than epsilon prime, you have all these curves. These are M curves, but they are so close that they look as only one. So and these have length 1. And so when you iterate k times, something that depends on your choice of epsilon will depend on this, but this is uniform because this has length 1, then you will reach the length that allows you to find some transversality. Okay, I also didn't say, so this projection, you can also bound the size of this M. It's technical. And then you'll see this bunch of curves, which will still be very close, but then they come back and they cross. So now you'll take the M curves you had before over here, and you will pick some curve here, which is in the same stable manifold. So when you continue to iterate forward, you will find the M plus 1 epsilon prime product. So this is much easier than the other argument. We don't need to control distortion or holonomies. And so that's it. So thank you very much.
Thank you very much, Rafael. Do you have any questions? Oh, wait a second.
So my question is, why the semi-conjugacy of lambda is a proper subset?
Because it's by contradiction, so I'm assuming the attractor is proper, and the semi-conjugacy always has injective points. So the repeller is mapped to everything, so the attractor cannot be mapped to everything.
But it's a semi-conjugacy.
Yes, but there are fibers which are injective. So, and you have compact set, they are bounded distance one from the other. So there are fibers which are smaller than this distance.
And why is the repeller mapped to everything?
Because it's saturated by the stable, which is minimal. So the stable is minimal, and it's a closed set. So it's.
Any more questions? Okay, so let's thank Rafael again. Ah.